Cool. Okay. Only like 18 minutes late. Not bad at all, right? Uh, so it's homework 9. Um, what did so I think like number 1 actually was what somebody in the chat was asking about, right? So we can talk about this for just a couple minutes. This one isn't too bad. It's just like kind of a lot of annoying algebra. So like, let me just show you what you want to do here essentially. The thing that I think people are forgetting here for this first problem is that when they say they have the same total kinetic energy, right, they're not just referring to rotational kinetic energy. They're talking about the total like translational and rotational kinetic energy. Yeah, I can look at problem 6 after this. So let's just do this though, because what we're saying, right, is like I'm not gonna use. Maybe I will, just because it might not be clear if I don't. Like all we're saying is that the kinetic energy of the sphere equals the kinetic energy of the cylinder, right? So we have to remember to include both forms of kinetic energy, right? That's something we have to do now. So what this ends up looking like, right, is we're gonna have they have the same mass, so we'll just call that M. They're gonna have their translational kinetic energy, except the thing is that they won't have the same translational velocity. So like this is what we do. We just do this. It's 1/2 I for the sphere, omega the sphere squared. So that's like for the sphere, obviously. And then the other part of this is just equating this, right, to the stuff for the cylinder. Which looks like this. So notice here that you can get rid of all the 1/2s and all the m's. Well, you have to actually substitute in for the moment of inertia to get rid of all the m's. But we can actually, I'll show you how I would do that. We'll take this one step further. Get rid of all the 1/2s. Now, I don't know if Hatridge mentioned this, but like there's this idea or like a technique, I guess, where you can write the moment of inertia for these objects, right, that we have like ready-made formulas for, like, you know, spheres and cylinders and disks and all that crap. We could just write it as like some coefficient, which I think is usually like alpha. Doesn't matter though, right? Times mr squared, right? Because like think about some of the ones that we have, like a disk, right? The moment of inertia for a disk is 1/2 mr squared. And so for the disk, alpha would just be 1/2. Let's say for a rod of length L, spinning about an axis passing through its center of mass, the alpha would be like 1/12. And so forth, right? So do people see what I'm saying here about this alpha thing? So this is kind of just like a little algebraic technique that lets us get rid of the masses and not have to start plugging in any gross numbers right just yet. So I think we all see here, right, the masses just drop out of this equation. And then all you really need to do from here is, let me just write this without the masses before I finish that thought. But it's just going to be using like the no slip condition, right? And remember that that was just like V, you could write V equals R omega. This is the no slip condition. Is this good? Do people kind of see what to do from here? Oh shit. I forgot to do this though. There should be these omegas, right? So don't forget about those because otherwise you'll be way off. So that should be good now. Are there any questions about this, or do people feel comfortable at this point about taking this to completion on their own? Because it is just algebra at this point, and I'd prefer not to do that for you. Are we good? Is anybody out there? Like, is my chat glitching? Okay, there we go. Cool. Okay. Let's see. So then the other one was number 6. Cool. Okay. Let's see here. This one, yeah. Nice. I'm so happy to have a biggest fan. So this is going to be this idea that like I don't think Hatridge really talked about based on like what some students have told me so far, that there are 2 forms of angular momentum, right? Sort of practically speaking. So let me just mention this, I guess, before we begin here. So like there's what we might call spin. Let's do it like this: spin angular momentum. And we could write this as a big S, maybe. And like, if this doesn't look like anything Hatridge has said or done, don't freak out, because like this is not really typically the way this is presented. But I'm doing it because I think there's some value to this. So this is of course a vector, right? And you could think of this as being like angular momentum that an object has when it's spinning about like an axis that passes through its body, right? So like the Earth, for instance, it makes a complete revolution in 24 hours. So there would be like spin angular momentum associated with that, right? Now, the other form is like what I would call orbital angular momentum. And this should be like what Hatridge probably focused on in lecture. And it's going to be given by cross product of position and momentum, right? So we could write this like this. Okay. Is this okay? Do people like see what I'm trying to say here? Because the total, say total angular momentum, we could call it J. I don't know, we're running out of symbols, so we could just say it's J, is like the sum of the orbital and the spin. Right, like this. And the point is that like this is going to be conserved in the first part of the problem here. That's why I'm talking about this, right? Not just I don't know, speaking because I like to hear the sound of my own voice. Well, yeah, that is. Remember that the RMV sine theta is just gonna happen because we define the orbital angular momentum via a cross product, right? So that's why when you want to just talk about the magnitude, you can write RMV sine theta. And that will be fine here because I guess we don't really care so much about like the vector nature of the orbital angular momentum, but it is there, right? It is a thing. But yeah, and nicely in this problem, actually, we'll see that theta is just 90 degrees, and sine of 90 is of course 1, right? So it's kind of like the sine isn't even there. So let's actually talk about what you do here. For like, let's just call it part A. Oops. We apply conservation of angular momentum, and this is going to be the total angular momentum, right? Because conservation of angular momentum most generally would look like J naught, the vector, equals J, the vector, right? And that's what we're doing here. So initially there is orbital angular momentum. The ball has it, right? And we could simply write, if we want to just talk about magnitudes, that let's do it like this. J naught is just L naught plus 0, right? Because I think they say the ball is not rotating. Yeah. So there's no spin angular momentum, right? It's just the orbital. And this is just, I'm going to switch the notation here because they're using like a ridiculous number of subscripts, in my opinion. But this is just RM, let's call it U naught for the ball. So U naught is the initial speed of the ball. For me, it's 12.8 meters per second. For you, it's whatever it's going to be, right? So that's that. Nothing is spinning, so we don't have to account for S, right? Now, what happens after? Let's call it just like J final. The ball's going to continue to move, right? What do they say? They say immediately after the collision, the ball still has a horizontal velocity of, for me, 5.10 meters per second in the same direction, right? So we still have that. We still have, like, we'll write RMU, where U is what they call V sub BF. Hang on, let me get to that in a second. And then this now will have, let's see here, because the topmost object, right? They keep calling it an object, but like I think it's pretty clearly a bottle, so I'm just going to say it's a bottle. Has an angular velocity of some number of radians per second about its center of mass, right? So the bottle has spin angular momentum now, and so we just write I'm just going to call it I, and then omega. And I think that's it. Let me just double check this. But for the collision, there is only orbital angular momentum. after the ball keeps going, it just slows down a little bit and the bottle starts to spin. Yeah, with some known angular speed about its center of mass. Yeah, this is it. So you just equate the two, right? We just say J naught equals J, and then you just do the stuff. I'll fill this in though, just so, because I like I said, I think that this is not something that Hatridge has mentioned or will mention at this point, right? But it's not saying like the spin angular momentum equals the orbital angular momentum or anything like that. Though, I mean, there are situations where maybe you could imagine, right, where you have something that has orbital angular momentum and then it's all sort of converted to the spin angular momentum, but that's not what's happening here because initially we just have the orbital, but after we have both forms. Is this making sense? Are we good with this for part A? It's just kind of doing the algebra now, right? I'm going to start talking about B, but if anybody has anything to ask about A, we can talk about that too. So here, I think like the easiest way to do this one is just to do conservation of linear momentum, right? You remember that? Because this is fine as long as we know the center of mass velocities of enough things, I guess. And I mean we have two velocities, right? The initial and final for the ball, and then we know it collides with the bottle, so we just have to apply conservation of linear momentum, right? So let's do that, see what it looks like. You can tell me if there is anything that's unclear about this, but I'm just going to say P naught equals P, and maybe we could just put X's in here to be sort of careful, but I think everybody sees that it is just in the X direction. And so the mass of the ball times U naught is the only source of linear momentum we have initially, right? Then after the collision, we're going to have the ball continues on, right? It slows down a little bit, but it's still moving in the same direction. And then I'll call the mass of the bottle big M. They call it M naught, but I'll just call it big M. And we could write that this is V for the center of mass velocity of the bottle. So it's just a matter of doing this. This isn't really that bad. I expect that like people who were struggling with this part probably just tried to make it more complicated than it kind of needed to be, which is sort of understandable because it's just a pure linear momentum thing, and we all probably feel like we should be done with that by now, right? Okay, is this good? Does anybody have any questions about this before we look at another problem? And if you want, like, go ahead and tell me. I think that, like, tell me which one you'd want me to look at next, but I think that, let's see here. Oh, number 10. I guess we'll get to number 10, yeah. Yeah, okay, cool. What do we have here? This awful thing. I mean, so this actually looks a lot worse than it is, I think. Let's see what we got here. Child's top is held in place upright on a frictionless surface. The axle has a radius of whatever. Two strings are wrapped around the axle. Top is set spinning by applying tension of constant tension to each string. It takes 0.680 seconds for the string to unwind. How much angular momentum does the top acquire? Yeah. Okay, so this is a little rusty for me, but I think that this is like, mm, this is like the rotational analog of the impulse momentum theorem, right? Where, let's see here. So impulse momentum theorem, right, said that P minus P naught equals F delta T. This should be F bar, right, because it's usually the average that we're thinking about here. Like this. So then what I want to say is we can just write something like L minus L naught equals the average torque times delta t, right? The time interval over which the torque is applied. And this should be average and okay, it doesn't say that it's at rest initially, but I think that's kind of what's happening here. But it doesn't even really matter because we could always just write this as delta L, right? So what we find is, well, that's it actually. It's just, I think it's just delta L equals the average torque times delta T. And the torque should be a constant, so we don't even have to worry about like taking an average or anything like that. Do people feel okay about computing the torque here? Is that possibly a source of confusion? Okay, that's fine. So it's actually really like nice of them to give you this kind of a diagram here because like look, this is the top view and basically the torque is caused by these tension forces and the nice thing is that uh, the angle here is 90 degrees, right? So like in our torque equals RF sine theta equation, the sine is just sine of 90, and that's 1, right? So the torque here, let's just do this. We'll say the net torque is going to be, and they give you, let's see, they give you, well, in the diagram, they give you the diameter, right? But they also give you the radius in the problem statement. So it's just it's just going to be, let's see, RT plus RT, right? So just 2RT. And because they say it's a constant tension, this means that the net torque is just the average torque, right? In our angular impulse, angular momentum theorem, right? Cool. Is this good? Are there any questions about this so far? Nice. Okay, then let's see. This other part, yeah, we can talk about the second part too, of course. This well, I mean, yeah, your torque should probably be small, right? Because the radius is given in like millimeters, so I don't think that shouldn't be too alarming. Let's see what we got here for the last part. This, it looks like will just be conservation of angular momentum, right? Because you have some value for L, right? Like the L that we just found essentially. Well, we called it delta L, but you know, whatever. So we could say this. We could say L naught equals tau bar delta T. And that is what you should put here. And then you're essentially given a way to figure out what L final is, right? So we just want to compute L final. And this will be I omega, right? And now we have to use this relation between the tangential velocity and the angular velocity, right? This v equals r omega thing again. We have to do, like, I guess we have to do a little bit of trig first. We have to note that, let's see here. Tangent of theta, right, equals h over r. So we find that r equals h over tangent theta, right? So that's one thing we have to do here, but that's just a little bit of trig. Hopefully it's not too bad. And the other thing is then just remembering that, as I was just saying, like v equals r omega, right? Like that. So then you can take this and this up here. And I'll just write one more thing here, I guess, but just because I know like this one looks really fucking bad, even though it's not like, I think it's not that bad once you sort of see like what to do, right? But let's say conservation of angular momentum gives, and we just have like tau bar delta t. I know it doesn't matter that I like write the bar this time because, as we discussed, like the net torque is the average torque, but it won't always be that way, right? So I just want to make sure I'm being careful when I write this stuff for you. This is the initial angular momentum, right? We saw that from part A, and this just equals I omega. So you divide both sides by omega, but you do have to like substitute, right? You have to do this stuff here. You have to like put in R and you have to put in V, though not necessarily in that order. But is this good? Do people see what kind of the next steps are here? I think we're pretty close to having done it, actually. It's just should be a little bit of algebra. Cool. Okay. I could probably do one more. Does anybody have anything else they want to ask about? Number 5, let's see what we got here. Okay, 5 seems to be popular. Yeah. This isn't so bad, but it does, like, it sort of, like, for me to, I think, explain this properly would require kind of making a sketch, which honestly I just don't want to do. But I'll talk you through what you do here. And of course, you know, if there are any questions, feel free to hit me up, and we'll get you sorted out. But the idea is like, so this is the process, right? We would think about the free body diagram. I'll put this in words, right? The free body diagram for the box should show a tension force acting upward and a gravitational force downward, right? Nothing surprising about this. Like, this is, you know, week 2, week 3 stuff, right? So there would just be this vector pointing up, corresponding to tension, and then one pointing down, corresponding to the weight. So that's probably cool. This other part could be a little bit more tricky, I guess, because we need to think about like the let's call it the free body diagram. I don't know, maybe like torque body diagram with a pulley. So I'll just say the diagram for the pulley should show a tension force let's see here. Should show a tension force acting tangentially on the pulley, right? Which we model as a disk. So what this means is like if this were my diagram, there would just be basically an arrow pointing straight down here, directed along the length of the rope that would be the tension force, right? So we're going to see, we have 3 things to solve for, but remember that the no slip condition tells us like if we have the radius of the object that's rotating and we have either the angular acceleration or the tangential acceleration, we have the other thing, right? So let me just leave that at that, I guess. And we can set these equations up. So easy one, right, is just going to be on the box in the y direction, we're going to have tension up. Let's call this one little m, mg down, right? This equals negative ma. Negative in here, just because we expect it to fall. And this sets us up to solve for the magnitude of the linear acceleration. So there's that. Then the net torque equation, right? And I'll just say about the z-axis is simply, let's see here. Well, it's just going to be RT, right? Because I just wanted to make sure that I'm getting the direction correct here. But this definitely will make the pulley tend to rotate counterclockwise, right? Which is our positive direction for rotations. And then we remember, right, that we want to set this equal to I alpha. Alpha. Holy shit. Okay, alpha. There we go. And they tell you, right, to model the pulley as a cylinder. Probably nothing surprising about that. So you just plug in the 1/2 mr squared for alpha. And the other thing, like the other thing that you need here, right, as I was mentioning, is just like the no slip condition, which tells us, so in as much as v equals r omega, we can write that a equals r alpha, right? So it looks like you have 2 equations and 3 unknowns, but it's actually just 2 equations and 2 unknowns because of this thing. All right, so do people kind of see what to do from here? Is this clear? Are we good? Okay, cool. I guess that didn't take really as long as I expected. Maybe I could look at one more, at least very briefly. I would kind of like to be done by 11, so we could use this time up. Does anybody have anything else? Three? All right, let's see what we got here. Yeah, this is a good one too, I think. This is, let's see here. This is just going to be conservation of energy, right? And so this is something that we've kind of seen before, but the difference is now that that the pulley can rotate. Well, no, that's not really the difference. But the difference is now that the pulley will have rotational kinetic energy, right, as it spins, because we're not neglecting the mass. So I'll just give you the outline here. Remember, right, just don't forget this stuff because it could be important, but like remember that when we do problems involving conservation of energy and there is gravitational potential energy that needs to be accounted for, we have to define where our y = 0 is, right? So don't forget this. And so let's say like y = 0 is where the center of mass of the second bucket is. I think that's a good choice here. So our initial energy is nice and easy. It's just going to be gravitational potential energy, right? Because it says the buckets are released from rest. So we could simply write M1G, and I'll call it H1. Yeah, I mean, I guess it is kind of already given for you. It's like what they call D naught. I'm calling it H1, but for me, it's the 1.75 meters. Yeah, yeah, they're kind of. I guess they are kind of defining it for you, so that's fine. But notice that like just because you're given a height doesn't necessarily mean that you have to choose your y = 0 based on that, right? But usually it would be fine. Okay, so then the final energy, right, is going to be, well, because basically these buckets are constrained to move together by virtue of the fact that they're connected with to each other with a rope. So however far down the larger bucket moves has to be how far the smaller bucket moves up, right? So we just kind of have that their gravitational potential energies sort of exchange forms, let's say. So now here we have M2G H2, right? Or H1 rather. We'll just call it H1. And the larger bucket is going to have kinetic energy, right? Translational kinetic energy as it hits the ground. That is pretty much given to you in the way the question is asked. So we'll just say this is 1/2 m1 v squared. And then we have to now, right, account for the fact that the pulley will have rotational kinetic energy at this point. So we would write 1/2 I omega squared, right? So people probably see where this is going at this point, but it's again going to be this thing where we just have to relate v and omega with the no slip condition. And in the problem statement, it says, right, assume that the rope does not slip on the pulley. And so that is about as clear of a hint as they could give you. You know what? That's a great question. I guess it would. Yeah, wow. Good catch. So yeah. So the question is, would the second bucket have kinetic energy moving up? And it seems like it's going to because as we just said, right, they're constrained to move together. So that was a slip on my part, but thankfully a vigilant viewer mentioned it. So what we would have to do is we'd have to add this m2v squared, right? Yeah, That's great. So then it's just solving this, right? And again, it's like you look at this and maybe you feel like you have one equation and two unknowns, but right, it just comes back to this no slip condition. This is, I think, what I was going to say before we talked about the kinetic energy of the other bucket. And we just would write that V equals R omega, right, where R is the radius of the pulley. And so then you get this down to one equation and one unknown. And strategically speaking, right, when you make your substitution, because you could substitute for V or omega, right? It doesn't, mathematically, it doesn't matter. But don't substitute out V because that's what you want to solve for, right? So just a little tip, but it doesn't matter because you can always, like, even if you accidentally solve for omega, then getting V is just a matter of doing this no slip condition again, right? Okay, cool. I guess that's it. This actually wasn't that long, but hopefully people found it helpful. You know, I gotta do my little spiel. If you haven't followed me already, please do. It helps. But yeah, other than that, I guess I'll see some of you tomorrow and then the rest of you next week. So have a good night, everybody.